up next, we've got market models, the AI brain behind autonomous pricing. And as you guessed it, we've just mentioned Dr. Uri Yerushalmi is here. Over to you.
Thank you, Simon. As Simon said, you might hear some concepts here taken from biology because my PhD is in computational neuroscience, and I will be using some terms inspired from algorithmic trading because my previous experience before founding Fetcherr is also based on algorithmic trading. So before we founded Fetcherr, we tried to understand how would the market look like where some of the players are truly based on state-of-the-art AI, where all of the decisions are based on data that flows continuously into the decision-making system. And here is the answer, as you might see it, that is based on true data on one of our customers, comparing their market before and after the system is deployed. The prices are much more variant because every product, every type of service gets its own attention. The prices are also not correlated one with the other because, again, humans do not bucket many products altogether, but different decision-making AI-based systems, different agents are paying attention to every different product. Every time some hint flows from the market, it causes a gradual reaction. And when all of these signals in the market are cross-validating each other, the reaction is much more pronounced. And the system is not only reactive to changes in the market, it is also proactive because it knows to anticipate the market impact of different decisions that are going to be made. And what enables that decision-making is a core model that is behind everything that I just described, a core market model that enables all of these decisions in real time. And that market model is based on same principles of other large deep learning neural network systems that you might know, like LLMs, like language models. The difference relates to the data on which these models are trained. Large language models are trained on textual data, and their output are tokens, are words in some sense. Large visual models like Nano Banana are outputting images and are trained on visual data. Same can be said about video models. We also know some large world models that are based on physical simulations of the world. And the large market model is based on the same techniques, but it is trained on market data and predicts future market dynamics. But having a predictive system that knows accurately what's going to happen next is not enough. For making actual decisions, we need to have a system that makes predictions and has the whole pipeline of decision-making system. And that's where we Fetcherr present M-Square, which is the decision-making platform for operational and commercial decisions to be made. And that platform includes a whole pipeline that starts with consolidation of data from various sources, using that data in order to train the market model that I presented before, until the market model gets into a state where it is trained enough and can predict the future market dynamics accurately. And then the market model is used to scan the space of possible decision-making policies and choosing the decision-making policy based on intensive simulations, choosing the one that is going to generate the maximal target of the business, for example, the best revenue, and inject the decisions into the right places of the business. Now, that can be applied on different layers of decision making and not only pricing. We are here talking about pricing specifically, but decisions can scan anything related to the inventory of the business, to the supply chain network of the business, and anything that is operationally and commercially a decision space that can influence the targets of the business. And when focusing specifically on pricing capabilities, these tools are not only covering and allowing 100% automation of pricing decisions, these tools, because of the fact that they are data-driven and then can optimize the decisions at scale, they enhance the competitive positioning of the enterprise or the business. Now, diving deeper into the different steps of the M-square pipeline, we can start with data consolidation. And when looking at different pieces of data, for example, one piece of data can be relating to the event data that can influence the demand. For example, we are using an event data provider that feeds its information into the system. And in that case, there was one event, Lollapalooza in South America. And the thing that is important in such system, because we are talking about deep learning systems, we are no longer using a certain event just as a row that an event has happened. An event has many dimensions. It has its location, it has its number of people that are going to attend the event, and each such attribute of the event influences the market model differently. A different type of event, for example, can be the Carnival Week. And the Carnival Week has some period in which it occurs, but the market model can understand from the occurrence of the event not only the impact on that specific period, but also the impact on the previous days, because many people are flying to the carnival or flying back afterwards, and the capability of the market model to gain information regarding the demand elasticity at very high granularity is very unique in such case. And events are only one type of input to many different types of data points that are feeding that neural net. We can maybe split the different types of data sets to the data sets that are proprietary, the business data sets, like the businesses' booking data, the different transactions, their prices, their shopping data from their website, and so on. And on top of that, we enrich that data with more public data. For example, news events that I showed before, weather data, and data from capital markets. And all of these data sets are feeding the market model so that the market model would be able to predict different attributes or different metrics of the market, like the demand magnitude, demand elasticity, cross-competitor elasticity, and so on. And that data is used to train the market model. And the market model is a deep learning model. And as a deep learning model, we can peek into the brains of that deep learning model and try to understand what does it pay attention to. So here is an analysis made on one of the market models of one of the competitors, where we see that if in mid-June one competitor joins the market, how does it redistribute the attention layers of the deep learning system across the different competitors? And we can see that the new yellow competitor gains some attention based on relocating attention from the other competitors based on the attributes of the different competitors in the market. And once the market model runs, it can output the anticipated future market dynamics. And here we get into the question of what is actually the output of such a market model, because output of image model are just images that are three-dimensional. Images have height, width, and color dimension. Outputs of large language models are tokens, but outputs of such market models are very hard to understand because they are multidimensional. They have the dimension of the transaction date, the dimension of the delivery date, the different dimensions that are encodings of the actual products, dimensions relating to price, and so on. So for viewing that by humans, we slice that multidimensional cube, which is the output of the market model. At certain points, for example, here, we can view the expected demand of a certain specific product, the way it is dependent on possible own prices and possible competitor prices that might be there. And these outputs are outputs that are purely data-based, data-oriented. They are not outputs that are engineered by data scientists on our side. And the beauty here is that the market model is capable understanding the difference between different markets. For example, markets that have a low impact of the competitors on the right side versus high impact of the competitors on the left side, or markets where the perceived value is higher than others, or markets where every cent matters, and that's reflected in the high resolution of the mesh of the heat map plot here. And we can also see how do market change and the elasticity curves of the demand. How does it change over time? For example, that's from recent dynamics in certain markets and the way the model reacted to fuel surges in the market. Because the fuel prices went up, the whole competitor landscape changed, and accordingly, the demand of the certain product changed to and react to the changes in the market. And once we have a market model that can anticipate future market dynamic, then we get into continuous simulations of scanning different pricing policies. And that space of pricing or decision-making policies is also a huge space that is multidimensional. And we always need to scan it and to stay on top of that space, always choosing the pricing policy that gains the maximal reward for the business. So here we can see a toy example where the decision-making policy has only two dimensions, and where we scan that space of possible decision-making policies and always make sure that we are making the decision that at the given time going forward is expected to generate maximal reward for the business. And once that decision is made, the system needs always to inject the decision into the right space, making sure that the decisions are continuously integrated for executions of the business. So that's where we get into a place where what I showed until now is a state-of-the-art decision-making system that is based on a heavy market model, but that's not enough. In order to actually gain the targets of the business, such a system needs to seamlessly integrate into the business and have an onboarding phase which has zero risk. And for that, we have built from scratch the Fetcherr system so that it would work with any type of data input, so that the onboarding would be seamless for the business, and that the outputs would be delivered for every different possible channel of such a business. And it was also said before, um, trust and confidence in such a system is a key. That's why such a system always makes sure that we have continuous performance metrics presented to the users. The system has inherently A/B testing measurement that are shown, where we always are comparing the products that we are controlling to products that we are not controlling, and we show proven results again and again through scientific A/B testing. And also part of the gaining trust to the system is that every decision is explained, because the system sometimes makes some decisions that are weird or alien in some sense. But for that, we have developed an explainability agent and explainability widget where every decision is well explained, where all of the factors that are influencing such a decisions are shown and listed. Now, such a system cannot fit all businesses the same way. That's why we have built such a system, so that it would adapt itself to the way the business is doing business. The business has the capability to define the goals, because not all businesses just want to drive for maximal revenue. In some cases, they are willing to sacrifice parts of the revenue in order to gain something else, like market share, or in some cases we need to focus more on profits because of expenses that are influencing the business. The users have full capability to guardrail the AI system, and to say where, even if the M square system thinks certain decisions should be made, to tell the system not to go there. For example, having some hierarchy of products price-wise, or always be above or below certain ceilings or floors of prices. And the users have full control over the autonomy of the system. They can define certain green zones in which the system can act on its own, and wherever the system hits some border of a green zone, the users might need to give approvals for such decisions. Our system currently gives the services to various businesses in different industries and businesses that are very different one from the other, size-wise, cost-wise, geographically, and in different metrics. One example that we are working with for many years are Azul Airlines. Currently, more over 70% of the airline is currently priced using our system. The system makes tens of thousands of decisions that are based on the same number of simulations every day. These are numbers provided by the airline. It saves thousands of analysts' hours, and that specific airline, for example, testified that they saw zero erroneous decisions made by such a system. And they are not the only ones. We see such numbers in many different customers, showing repeatedly 7% of revenue uplift, 96% of accuracy, and more than 60% savings of human working hours. Thank you so much.